Some stars are so massive they burn millions of times brighter than the sun and end their lives in explosions that scatter the very atoms that make up your phone, your blood, and the gold on your ring. You'll see how these giants are born, how they keep themselves alive with a furnace at their core. Think of fusion as a campfire that turns light gases into heavier ones, and why gravity eventually squeezes them so hard that they either blow apart in a cosmic firework or collapse into a tiny, insanely dense object. A supernova is just a giant stellar fireworks show, louder, hotter, and with bigger consequences than anything on the 4th of July. To make it simple, imagine a pressure cooker where the lid is gravity. When the cooker's contents change too much, something has to give, often very dramatically. By the end you'll know how the elements around you were forged, why some stars leave behind black holes, and what these dramatic finales mean for galaxies, all without heavy jargon, just clear visuals, everyday analogies, and a little humor. Stars don't take long naps, they go out with a mic drop. Stick with me for spectacular images, surprising connections to life on Earth, and an explanation that actually makes sense. The big picture: why massive stars matter. Massive stars drive the chemical richness of the universe by building heavier elements in their cores and then tossing those materials back into space. Inside a star, light atoms stick together to make heavier ones through a process called fusion. Think of it like atoms being squeezed together in a cosmic pressure cooker, releasing energy as they do. Those newly made elements include the oxygen we breathe, the carbon that forms the backbone of life, and the iron in your blood. Without massive stars making and spreading these ingredients, planets and life as we know it would be nearly impossible. When a massive star reaches the end of its fuel, it often explodes in a bright, powerful blast called a supernova. That word sounds dramatic because it is. The explosion rips the star apart and scatters its guts across space, seeding nearby clouds of gas and dust with metals and other elements. These shock waves can compress gas and help start the birth of new stars, so in a very real sense a single massive star can plant the seeds for an entire stellar neighborhood. Picture a gardener tossing seeds into a field, chaotic, noisy, and strangely fertile. Short sentence. The leftovers of the blast may shrink into a neutron star, an object packed so tight a teaspoon would weigh more than a mountain, or collapse into a black hole, where gravity gets so strong not even light can escape. Beyond making elements and spawning new stars, massive stars shape their surroundings while they live. They blast intense light and fast winds of particles that carve bubbles in the gas around them, often creating spectacular shapes in nebulae. These winds and light can either trigger new star formation by squeezing clouds or slow it down by blowing gas away. They act as both creators and regulators, like a stern teacher who also hands out gold stars. Their energetic output also produces cosmic rays, tiny particles that zip through space and can interfere with electronics on satellites and airplanes, which is something engineers have to plan for. Studying massive stars and their deaths gives scientists a chance to test physics under extreme conditions that cannot be recreated on Earth. Astronomers use the explosions and remnants as natural laboratories to understand how matter behaves at enormous pressures and temperatures. Practical payoffs are real. Knowledge about cosmic radiation helps protect astronauts and sensitive spacecraft components, and knowing where heavy elements come from informs models of planet formation and the likelihood of life-friendly worlds. So although these stars live fast and die young, their role in making planets, providing materials for technology, and shaping galaxies is enormous, and a little bit dramatic, which keeps astronomers well entertained. Stellar nurseries and cosmic cradles. Cold, dense clouds of hydrogen gas mixed with tiny grains of dust are the birthplace of stars. These clouds are so cold that the gas slows down and can clump together, and the dust makes them look dark against the bright background of the galaxy. Light has trouble getting through, so astronomers look at infrared and radio waves to peek inside, kind of like using a thermal camera to see through fog. You can think of the dust grains as the specks that help droplets form in a cloud, only much bigger and much slower. In everyday terms, it's a bit like how tiny seeds in a loaf of bread help the dough rise into something solid. Pressure and gravity are the main players that decide what happens next. In parts of the cloud where the gas gets denser, gravity starts pulling material inward and a small region collapses into a rounder, hotter blob called a protostar. Turbulence in the cloud stirs things up and makes clumps, while magnetic fields thread through the gas and can slow the collapse, acting like cosmic seatbelts. Sometimes an outside shove, like the shock wave from a nearby massive star or a collision with another cloud, triggers the collapse, similar to how a sudden gust of wind can topple a stack of unsteady boxes. As the protostar gathers material, it often develops a flattened spinning disk around it. That disk feeds the young star and can later form planets. Jets of gas shoot out along the star's poles, clearing paths through the surrounding cloud and making spectacular, narrow beams that glow when they slam into nearby gas. Many stars are born in groups, sharing the same cloud, so a newborn star can have neighbors forming at the same time. This cluster behavior means stars often start life in crowded conditions, like kids in a playground fighting over swings. The big, attention-hungry ones quickly change the neighborhood by blasting out light and winds. Observations with modern telescopes reveal pillars, bubbles, and glowing shells where stars are actively forming, offering direct evidence of these processes. The local environment inside a cloud helps determine whether a star will be small and long-lived or massive and short-lived, and that in turn affects the future of the region by enriching it with heavier elements when the biggest stars end their lives. In practical terms, stellar nurseries are cosmic recycling centers. Gas and dust gather, make stars, and planets, and later get stirred and returned so the next generation can form. Think of it as gardening on a galactic scale, but with less weeding. And yes, gravity and time are the tireless caretakers. They don't take coffee breaks, though they probably should. How a massive star is born. Giant clouds of cold gas and dust in space act as stellar nurseries, and massive stars begin life inside the densest lumps of these clouds. These clouds are mostly hydrogen, with tiny dust grains mixed in that help the gas cool and clump together. When a region becomes dense enough, gravity wins and the lump starts to fall inward. Think of it like a snowball rolling down a hill and gathering more snow, only in space the snow is gas and the hill is invisible. When the pull of gravity overcomes the gas pressure and the gentle push of heat, collapse speeds up and a compact core forms. As that core contracts, it spins faster because of the same effect that makes a figure skater twirl more quickly with arms pulled in. The spinning gas flattens into a disk around the growing center, and material from the disk spirals inward, feeding the protostar at the middle. This process of material falling in is called accretion. The inflow can be steady or messy, with chunks of gas, streams, and sometimes smaller companions. A simple kitchen example helps. Stirring batter makes it swirl and dip toward the center. The batter is the gas, and the center is where the future star is being made. Massive stars pull in gas much faster than their smaller cousins because their gravity is stronger, so they build up mass quickly. That rapid growth creates a problem. As the center heats up, the forming star begins to emit intense light that pushes outward and can oppose further infall of gas. Nature finds workarounds. The disk channels incoming gas along its plane where the light and wind are less effective, and narrow jets shoot out along the poles to shed extra spin and excess energy. In very crowded nurseries, close encounters or even mergers between protostars can help assemble very massive objects. Astronomers think this happens in the densest stellar creches. Soon the core becomes hot and dense enough for hydrogen nuclei to fuse, releasing energy that turns the newborn into a shining main sequence star. Massive newborns are bright and hot, blowing bubbles of ionized gas around them. These glowing bubbles are like giant neon signs announcing their presence. Their fierce winds and radiation can erode nearby gas, sometimes stopping nearby stars from forming, and sometimes squeezing clouds to spark new collapses. In that way they are both demolition crew and midwife. The whole birth is a dramatic, noisy affair by cosmic standards, and it sets the stage for a short but spectacular life. Fusion engines and the main sequence lifestyle. At the heart of a main sequence star, hydrogen is being steadily turned into helium by a process that releases a prodigious amount of energy. That energy is what makes the star shine. Gravity squeezes the core inward while the heat and pressure from fusion push outward, and the two forces hang in a tidy balance that keeps the star from collapsing or exploding. think of it as a cosmic tug-of-war that nobody wants to lose. This steady energy output is what people mean when they call fusion the star's engine, fuel in, light and heat out. It's like a car engine that converts gasoline into motion, except the fuel is hydrogen and the motion is light. Smaller, cooler stars use a simple, reliable fusion pathway where protons combine step by step to build helium. The Sun does this and it's called the proton-proton chain, which just means protons team up slowly and patiently. Bigger, hotter stars switch to a different helper-driven route called the CNO cycle. Carbon, nitrogen and oxygen act like catalysts that speed things up, so the heavyweights have a more aggressive engine. The difference is temperature. Higher core temperatures favor the CNO cycle, while lower ones make the proton-proton route the efficient choice. You can compare it to cooking. Some recipes need a long simmer, others require a hot wok and fast stirring. Mass controls the whole lifestyle. More mass gives a star a more powerful engine, making it much brighter but burning through its hydrogen fuel far faster. Less mass means a quieter, dimmer star that stretches its fuel over a very long time. Picture a bonfire versus a candle. Both give heat and light, but the bonfire roars and dies faster, while the candle glows steadily for ages. Because brightness and lifetime are linked, the heaviest stars live fast and luminous, whereas the smallest main sequence stars are slow, thrifty burners. Energy created in the core has to travel outward before it escapes as the light we see. Sometimes that journey is a slow photon shuffle, with tiny packets of light bouncing through the star's dense layers as if in a crowded hallway. Other times the hot gas itself moves, carrying heat outward like the boiling motion in a pot of soup. The star's surface temperature, which results from how much energy reaches the exterior, sets its color. Cooler surfaces look red, hotter ones look blue-white, simple and observable. That surface color and brightness are the handy clues astronomers use to tell where a star sits in its main sequence lifestyle. Most stars spend the majority of their lives in this steady phase, quietly fusing hydrogen in their cores. The Sun is a typical example and provides a living demonstration of these principles. Its steady light, warmth, and predictable behavior show how fusion engines run day in and day out. If you want a practical comparison, think of household appliances. Some run on low power for a long time, like a refrigerator, others use lots of power for short bursts, like an oven preheating. Stars behave the same way, only much grander and with a little more drama when the fuel finally runs out, so enjoy the light while it lasts, because even engines as massive as stars have a life cycle. The drama of shorter lives. Massive stars burn through their nuclear fuel much faster than their smaller cousins, because being huge makes them hotter and brighter. They can weigh many times more than our Sun, which means they are under intense pressure in their cores. Picture a marathon runner compared to a sprinter. The sprinter uses energy wildly and finishes the race quickly. The result is a short, dramatic lifetime rather than a slow, steady one. At the heart of every massive star, lighter atoms fuse together to make heavier ones, releasing enormous energy in the process. Fusion is like cooking, combining simple ingredients into something heavier and hotter, and that heat is what makes the star shine. This process continues, building heavier and heavier elements in nested shells, until the core is filled with iron, an element that refuses to give back energy when forced together. When the core can no longer produce energy to hold off gravity, it collapses inward almost instantly. The collapse is sudden. The rebound and the violent upheaval following it is what makes a supernova. A supernova is a cosmic explosion so powerful it spreads the star's forged elements far into space, seeding future generations of stars, planets, and even living things. The iron in a wristwatch, the calcium in bones, and the gold in a ring all trace their ancestry to such stellar deaths. Left behind after the blast are compact remnants, sometimes a neutron star, which is an unimaginably dense ball of neutrons, and sometimes a black hole, a region where gravity is so strong that not even light can escape. You can think of a neutron star as something like a city crushed into a sugar cube, weird, tiny, and extreme. Those massive stars also shape their surroundings long before they explode. Powerful stellar winds and intense light carve out cavities in the gas and dust around them, sometimes pushing on nearby clouds and nudging new stars to form. Astronomers see these effects as glowing bubbles and pillars of gas in star-forming regions, glowing like campfires surrounded by sparks. The same forces that shorten a massive star's life can also act as a midwife for the next generation of stars. Life for these giants is fast, loud, and consequential. They don't stick around to watch the long-term outcomes, but their brief existence sets the stage for planets and chemistry that support life. And for a little cosmic irony, living fast and dying spectacularly is exactly how the universe makes the building blocks we use every day. Element factories, building the periodic table. Massive stars make new chemical elements by smashing lighter atoms together in their hot cores, and those products become the raw material for planets, people, and peanut butter. In the center of a big star, hydrogen atoms fuse into helium, and when hydrogen runs low the star switches to fusing helium into carbon and oxygen. Further burning stages build still heavier elements in successive shells around the core. This layered structure is often called an onion by astronomers because each shell burns a different fuel, hydrogen on the outside, then helium, then carbon, oxygen, and so on. Oxygen and carbon are two everyday examples of stellar products. Oxygen fills our lungs and carbon is the backbone of the molecules in your body. Fusion in these shells keeps the star shining because each combination of lighter nuclei into a heavier one gives off energy, until iron. Iron is special because combining or splitting iron doesn't give energy back, it takes energy instead. That means a star cannot gain pressure support by fusing iron, and once a massive star builds a core made of iron the balance that held the star up fails. When that happens the core collapses and the outer layers explode outwards, a violent process that flings the star's built elements into space. A well-known outcome of this explosive chemistry is nickel-56, a radioactive isotope that decays into iron-56 and helps power the bright light we see from some supernovae. Heavier elements than iron mostly arrive by adding neutrons to existing nuclei rather than by fusion. There are two main ways this happens: a slow, steady neutron capture process where atoms pick up neutrons one at a time and then sometimes change a neutron into a proton, and a rapid process where a flood of neutrons hits nuclei so quickly that many are added before any decay can occur. The slow route, occurring in certain burning shells of massive stars or in other giant stars, makes elements like strontium and barium. The rapid route needs extremely neutron-rich, violent conditions, and is responsible for producing very heavy elements such as gold and uranium. Astronomers now know these bursts of creation happen in explosive places like collapsing stars and collisions between neutron stars. If you like jewelry, then you indirectly owe a debt to those brief, chaotic fireworks. Once made, the elements are recycled, steady stellar winds and sudden explosions scatter them into the surrounding gas, which later condenses to form new stars, planets, and eventually life. Common materials on Earth have stellar origins: the iron in your blood, the calcium in your bones, the carbon in your DNA, and the oxygen you breathe all began inside stars. Astronomers identify which elements were produced by reading the fingerprints of light from stars and supernovae. Each element leaves a distinctive pattern in the light that betrays its presence. So when you flip on a silicon-powered device or admire a gold ring, remember that massive stars acted as cosmic factories, mixing, baking, and sometimes exploding to assemble the periodic table items we use every day, and yes, they can be dramatic cooks. Internal battles, radiation, convection, and turbulence. Deep inside a massive star, the energy born in the hot core has to find a way out, and the method it chooses shapes the star's life. Photons, packets of light, carry energy outward by bumping around in a crowded atomic soup. When the material is dense and opaque, those photons do a long random walk and act like tiny, impatient commuters stuck in a busy subway. Opacity, which is how foggy the stellar gas is to light, decides whether radiation can slip through easily or gets trapped for a long time. In very massive stars, the pressure from light itself becomes important and actually helps hold up some layers against gravity, so light is not just a messenger but also part of the scaffolding. Hot gas can also move as a whole, not just by light. Convection is that process, blobs of warmer, less dense material rise while cooler, denser material sinks, like the rolling cells you see when a pot of soup comes to a boil or the blobs drifting in a lava lamp. In massive stars, the center where hydrogen fuses is often convective, meaning fresh fuel is regularly stirred down toward the hottest regions and ash is mixed outwards. That stirring changes how long burning stages last and what elements end up in which layers. It's a lot like stirring sugar into coffee so that the sweetness reaches every sip instead of sitting stubbornly at the bottom. Then there is turbulence, which is what you call motion when it loses any neat pattern and becomes chaotic swirls at many sizes. Turbulence is born when convection speeds up, when different flow layers slip past each other, or when shocks pass through the gas. Think of eddies behind a rock in a fast stream or the messy whirlpool that forms when you pull the plug from a bathtub. Inside a star, turbulence mixes material across boundaries that would otherwise stay separate, seeds asymmetries, and can amplify instabilities. Those messy motions matter a great deal in the final stages of a massive star's life. They help determine how the core collapses and how the eventual explosion is shaped, because chaotic flows can make it easier for energy, particularly from neutrinos and turbulent pressure, to push back against infalling material. These three players, radiation, convection, turbulence, are constantly arguing and teaming up. In layers where radiation escapes quickly, convective motion is suppressed. Where photons get trapped, convection takes over as the dominant transport. Turbulence can enhance or quench convection depending on the situation, and both convection and turbulence can change the star's surface by dredging up fusion products so observers see unusual surface chemistry or variable brightness. In practical terms, this interplay affects things we can measure: the spectrum of a star, the speed and clumpiness of its wind, and the shape of the supernova remnant left behind. Stars, it turns out, are messy eaters. Light tries to sneak out quietly, bulk flows stir the pot, and turbulence makes sure there's always a little chaos at the table. Stellar winds and losing mass in style. Massive stars continuously lose material through powerful outflows, a bit like a giant person sweating steadily under a hot lamp. This loss happens because the star is so luminous that its light can actually push gas away, and because the outer layers are often unstable and boiling with convective motions that loft material into space. Radiation pressure, simply the push that light exerts, can accelerate atoms and ions until they escape the star's pull. Faster rotation or magnetic fields can help fling material outward, and in tight pairs of stars a companion can pull off whole layers like a jealous roommate stealing your snacks. Astronomers read the fingerprints of these winds in starlight. When gas streams away, the spectrum of the star shows telltale signs. Some wavelengths are dimmed while others glow, patterns that reveal gas moving toward us or away from us. Telescopes that see infrared light spot warm dust created by outflows, while radio telescopes trace cool, extended gas. Real examples include hot, stripped stars known as Wolf-Rayet stars, which display strong emission from dense, fast winds, and extreme cases like Eta Carinae that have blown off massive shells visible as glowing nebulae. These observations let scientists map not just that a star is losing mass but how fast and in what style. Losing mass changes everything about how a massive star lives and dies. As outer layers are peeled away, the internal balance shifts, exposing deeper layers and altering the chemical mix seen at the surface. This is important because the core's mass and composition decide whether the star will end as one kind of explosion or another, and whether the remnant will be a neutron star or a black hole. The winds also slow the star's spin over time, like someone shedding a heavy backpack before attempting a sprint. Material blown off enriches the surrounding space with heavier elements and dust, supplying the raw ingredients for future generations of stars and planets, rather like a gardener composting last season's leaves to feed new seedlings. Not all mass loss is polite and gradual. Some stars erupt spectacularly. In those cases, a star can dump huge amounts of gas in a short period, throwing off shells and creating dramatic visible structures that last for thousands of years. Steady winds carve bubbles and cavities in the interstellar medium, while violent eruptions build dense shells that glow and collide with older material. Both modes matter. Steady winds quietly shape a star's slow evolution, and eruptions rewrite its near-term destiny. For a cosmic comparison, think of steady winds as a daily haircut and eruptions as suddenly shaving your head, different looks, both transformational. Everyday analogies help make sense of these processes. A blowing dandelion shows how small particles can be carried away on a breeze, a hairdryer loosens and lifts dust like radiation pressure does to atoms, and composting shows how lost material becomes the building blocks for new life. Humor aside, mass loss is not mere cosmetic trimming for massive stars, it is a core, observable, and decisive factor in their life stories, one that astronomers study across many wavelengths to understand how the biggest stars return their riches to the galaxy. The art of stellar rotation and magnetic fields. Spinning changes the inside of a giant star in ways you can picture if you've ever stirred a pot of soup. The motion carries fresh fuel toward the hot center and moves processed material outward. Fast internal rotation mixes hydrogen down into the core so the star can keep burning longer, while slower rotation lets layers stay separated like a layered cake. The change in shape is real too. Centrifugal force makes a rapidly spinning star bulge at the equator, like a slightly flattened soccer ball. In everyday terms, think of a pizza maker tossing dough. Faster spin stretches things outward and changes how the dough cooks, just as stellar spin alters how a star burns. Magnetic fields grow from moving charged gas inside the star, working like an internal generator often called a dynamo. This simply means the moving material creates and reshapes magnetic lines. Those magnetic lines act like invisible elastic bands that can link different layers, carrying braking forces that slow the outer layers by pulling on the stellar wind. A useful household comparison is hair on a windy day. Static electricity and motion make strands stick and pull. Stellar magnetism similarly tugs and rearranges gas. As a result, magnetic braking can rob a star of spin over time and redirect mass loss into columns or disks rather than a smooth breeze. When rotation and magnetism team up, surprising outcomes appear. Magnetic fields can transfer angular momentum, think of it as rotational oomph, from one part of the star to another, smoothing out differences and sometimes allowing the core to keep more spin. Rapidly rotating, well-mixed stars may follow a one-pot evolution where the whole star stays similar through its life. Those stars can die in ways that favor narrow, focused outflows or jets. In some deaths, the collapsing core's rotation and intense magnetic fields work together to launch powerful, narrow beams of material, which is one proposed route to the long, bright flashes astronomers call gamma-ray bursts. Picture twisting a wet towel hard enough that the water shoots out in a concentrated stream. Rotation plus magnetism can focus a star's final blow in a similar manner. Remnants show the effects loud and clear. Pulsars, which are compact stellar leftovers, sweep beams of light like cosmic lighthouses because their rotation turns hot magnetic poles in and out of view. Even more extreme are magnetars, objects left behind with magnetic fields so strong they squeeze and crack the outer crust, producing bright bursts of 10th rays and gamma rays. The magnetic stress is the culprit rather than leftover heat. Observationally, astronomers spot rapidly spinning massive stars by emission disks and telltale surface chemical patterns that reveal internal mixing. Surface layers enriched with fusion products are a fingerprint of rotation-driven blending. All this matters practically. Knowing how spin and magnetism work helps predict what type of explosion a star might produce, which elements get forged and flung into space, and whether the collapsed core will become a neutron star with a dramatic magnetic personality or quietly settle into a black hole. Simple analogies help keep the picture clear. Stirring mixes fuel, magnets tie layers together, and fast spinning throws material outward. Scientists use these ideas to model outcomes and compare them with real observations, refining their understanding as telescopes catch more examples. A little humor helps too. Stars may be gigantic, but when they argue about who should spin faster, the whole galaxy hears the fireworks. When fuel runs low, core contraction. As a massive star uses up the material that powers its inner furnace, the outward push that fights gravity weakens and the core starts to squeeze inward. This inward squeeze is driven by gravity, which is always trying to pull the star into a smaller ball. Fusion, the process that turns light atoms into heavier ones and releases energy, supplies the push outward. When that supply drops, the balance tips. Think of it like a hot air balloon losing burner flame, the lift falls and gravity wins a little ground. The squeezing heats the core. Pressure rises because packing the same stuff into a smaller space makes it hotter, just like pumping air into a bicycle tire heats the pump. That higher temperature can light new kinds of fusion in surrounding layers, burning heavier fuel than before, but only if the core gets hot enough. Layers form, one on top of another, like an onion with different reactions happening in each ring. Some layers may start burning while the center continues to contract, so the star's interior becomes a complex stack of activity. A strange kind of resistance can show up when things get extremely crowded. Electrons, the tiny particles around atoms, don't like being squeezed together and begin to push back in a way unlike ordinary pressure. Scientists call this degeneracy pressure, but a simple way to picture it is a packed subway car where people can't occupy the same space and so resist getting any closer. In many massive stars, this electron push is not strong enough to stop the squeeze for long. The core keeps compressing, temperatures climb even higher, and the star moves on to try fusing ever heavier material, until it reaches types that no longer give back energy when fused, notably iron. That's the natural limit of useful burning. Energy also sneaks away in hard-to-see forms during contraction. Tiny particles called neutrinos are made in abundance as the core gets denser and hotter, and they stream out carrying energy with them. Because neutrinos interact so weakly with matter, they are like guests who quietly leave the party without saying goodbye. The net result is the core loses support and contracts further. On the outside, the star reacts, burning in shells can brighten or puff up outer layers, and the whole object can change its appearance. In everyday terms, it's a bit like taking the heat off a pressure cooker. Internal changes alter how steam escapes and how the pot looks. This inward squeeze is a race between two things: getting hot enough to start new fuel-burning reactions, and running into a point where no more useful fusion is possible. It's an elegant, if dramatic, struggle. A massive star's core may briefly ignite new fuels as it contracts, but each step yields less time and less payoff. A final squeeze leaves the core with fewer options, and that sets the stage for the star's next big act. Meanwhile, astronomers watch for shifts in brightness and other subtle clues that the interior is changing, like listening for distant heartbeats in the sky. The changes are real, often fast compared to the star's earlier life, and a little bit theatrical, as if the star, having burned through its grocery list, is now rummaging the pantry for anything that will keep it going. The final fusion stages: iron and instability. Deep in the center of a very massive star, nuclear reactions grind through lighter elements and keep creating heavier ones until iron piles up in the core. This is not a matter of taste. Iron represents a stopping point because fusing lighter nuclei into elements lighter than iron releases energy, while trying to make things heavier than iron actually consumes energy. Think of it like climbing a hill while getting rewarded with sunshine at each step up, and then suddenly hitting a flat spot where you have to pay tolls to keep going. That change in the energy balance is the practical trigger for everything that follows. As the iron core grows, it becomes heavier and more squeezed. Electrons, tiny particles that ordinarily keep space between atomic nuclei, get pushed so close together that they start to resist being packed any tighter, like people all insisting on personal space in a crowded elevator. That resistance can hold the star for a while, but once the core becomes too heavy, the squeeze becomes unstoppable and the resistance fails. At the same time, the environment grows so violent that high-energy light can shatter iron nuclei back into smaller pieces, and some electrons are forced into protons, forming neutrons and releasing ghost-like particles called neutrinos that slip away carrying energy. These processes steal pressure and heat from the core, removing the support the star needs and tipping it into sudden collapse. Collapse happens extremely fast and powerfully. The core plunges inward until the material is packed into a tiny, extremely stiff ball made mostly of neutrons. When the infall hits that stiff center, the innermost layers rebound and a shock wave races outward. That shock by itself often slows and stalls, because the falling outer layers sap its strength. Luckily for the star's dramatic exit, the flood of escaping neutrinos, those nearly invisible particles, can reheat matter behind the stalled shock and give it the shove needed to blow the outer layers into space. It is rather like trying to open a stuck door. One person pushes, another flashes a flashlight, and a gust of wind finally swings it wide. The whole event turns a stable, glowing star into either a compact neutron ball or, if the core is too heavy, a region where gravity wins completely and light itself cannot escape. The instability of an iron core is therefore both the end of steady energy production inside the star and the starting pistol for cosmic recycling. The explosion that follows breaks heavy nuclei into new ones and forges many of the elements heavier than iron, while ejecting them into space where they later become part of planets, rocks, and even our own blood. So the iron that makes a kitchen pan or runs in your bloodstream likely began its journey inside a massive star and was hurled outward by the very instability that ends such stars' lives. A little dark humor is in order. The star's final act is messy, loud, if you could hear it, and remarkably productive, nature's version of demolition with recycling. Supernovae explained, cataclysmic endings. Supernovae are giant stellar explosions that mark the dramatic end of some stars, releasing more energy in a short time than a star normally does over its whole lifetime. One common route to this blast happens when a very massive star runs out of fuel in its core and can no longer hold itself up, the center collapses and the outer layers are hurled into space. Another route involves a small, very dense star stealing material from a nearby companion until it can no longer stay stable and then detonates in a runaway reaction. Think of the first like a car engine suddenly seizing when it runs out of oil, and the second like an overstuffed suitcase that finally bursts open at the baggage claim, both messy, both dramatic. As the collapsing core slams inward, it can bounce back and drive a shock wave that tears the star apart, or in the case of the fuel-stealing event the whole object ignites in a thermonuclear fireball. Either way the result is an enormous flash of light. That flash can be so bright that it momentarily outshines the rest of its home galaxy. Telescopes that see visible light, radio waves, ultraviolet and 10th rays all watch for these sudden appearances. Tiny, hard-to-detect particles called neutrinos also rush out and can be caught by underground detectors, acting like whispering witnesses to the explosion. Those explosions are cosmic factories, building and scattering many of the chemical elements heavier than helium. Elements such as iron, calcium and nickel are forged and thrown into space, mixing into clouds of gas and dust that later collapse to form new stars, planets and even the raw material for life. The iron in your blood and the calcium in your bones owe their existence to generations of stars that exploded long ago, which is a poetic way of saying your body has been recycled by the galaxy. Left behind are glowing remnants, tangled clouds of gas that look beautiful in telescope images and serve as signposts of where the blast occurred. Astronomers rely on certain supernovae as practical tools, because some of them have a predictable brightness that helps measure distances across the universe. Observations across different types of light give clues about what kind of star blew up and how the explosion unfolded. Nearby supernovae are rare enough that they are not a daily hazard to Earth, but when one does occur in our neighborhood it becomes a key event for scientists to study fundamental physics under extreme conditions. And while the universe's fireworks can be dangerous up close, on the whole they are the cosmos's version of recycling with style, loud, bright, and oddly helpful to future generations of stars. Remnants revealed, neutron stars and black holes. Massive stars often end their tidy lives by leaving behind something small and extreme. Neutron stars are tiny compared with ordinary stars but incredibly dense, pack roughly the mass of our Sun into a sphere only about 10 to 20 kilometers across and you start to get the idea. Think of a city-sized ball that contains as much material as a star. It's hard to picture, yet that's the scale. A pinch of that material would outweigh entire mountains, so a sugar cube-sized sample would feel like a very bad idea to carry home. These compact objects are mostly made of neutrons squeezed together so tightly that normal atoms cannot survive. Sometimes they spin very fast, hundreds of times per second in extreme cases, and sweep beams of light and radio waves out into space like a cosmic lighthouse. We call those pulsars. You can liken a pulsar to a spinning flashlight at a beach party. The beam flashes past you at regular intervals, and radio telescopes on Earth register those regular beats. Astronomers use these steady flashes as precise clocks to study everything from the motion of nearby stars to the faint wobble caused by orbiting companions. Black holes are the other dramatic outcome, and they push gravity to the limit. Put simply, a black hole is a region where gravity becomes so strong that nothing, not even light, can escape once it gets too close. The boundary beyond which escape is impossible is called the event horizon, which acts like an invisible point of no return. You can compare it to a very steep waterfall. Once you go past the edge, no amount of swimming will get you back upstream. Stellar black holes form when massive stars collapse and can have a few to many times the Sun's mass packed into a surprisingly small volume. At the centers of galaxies, much larger, supermassive, black holes sit and influence the motion of entire star neighborhoods. Detection is mostly indirect because you can't see a black hole itself. When gas and dust fall toward a black hole, they spiral in and heat up, shining brightly in 10th rays before crossing the event horizon. Telescopes catch that glow. In binary systems, a black hole can pull matter from a companion star, creating a bright disk that looks ostentatious compared with the black hole's invisibility. Neutron stars also announce themselves by their pulses and by producing bursts of high-energy radiation when star matter slams onto their solid surface. Another way to reveal these compact remnants is by watching how nearby stars move. If a star orbits something invisible and massive, that invisible thing is a strong suspect. There are dramatic, real-world consequences from these tiny leftovers. Strong magnetic fields near neutron stars can be trillions of times stronger than Earth's, and they can strip atoms apart. In the lab, we can't recreate such conditions, so these objects are natural extreme physics experiments. Black holes, meanwhile, can launch jets of particles at nearly the speed of light that stretch far beyond their host galaxy, a bit like a fire hose blasting out into space. Humorous as it sounds, both objects are cosmic rule breakers. They take familiar physics and push it until new effects appear. Scientists study them by combining visible light, radio waves, 10th rays, and even ripples in spacetime itself, building a complete picture from these different clues. Every observation adds a practical piece to the puzzle. Timing variations from pulsars help test how gravity behaves in extreme conditions, and measurements of how gas behaves near a black hole teach us about how matter behaves when pushed to its limits. For everyday comparison, studying these remnants is like stress testing the universe. You squeeze things to extremes and see what snaps or holds. And while they sound fearsome, both neutron stars and black holes are far away and do no harm to us here on Earth. They are remarkable natural laboratories that let humans learn about physics well beyond the reach of kitchen experiments. Exotic outcomes, hypernovae and gamma-ray bursts. Some of the most massive stars don't just explode, they unleash blasts so fierce they can briefly outshine their entire host galaxy. These extreme explosions, often far stronger than the usual stellar blasts, come from a collapsing core that forms a black hole and drives narrow, powerful jets of radiation out into space. Gamma rays are the kind of light these jets emit. They are the highest energy light and are so energetic that our atmosphere blocks them, which is why only space telescopes can catch the show. Satellites such as Swift and Fermi watch the sky for these sudden flashes and then point other telescopes to study the fading glow that follows. The basic way this works is fairly simple. A very big star runs out of fuel and its core falls inward under gravity. If the collapsing core spins quickly and channels energy into focus streams, those streams punch through the star and blast into space like a cosmic fire hose. Not every dying star makes such a jet. Think of it like two different kitchen scenes. A popped balloon scatters confetti everywhere, a normal supernova, but a garden hose aimed through a paper tube shoots a tight, powerful stream, a gamma-ray burst. Fast spin, strong magnetic action, and a lack of a thick outer envelope are part of the recipe that lets the jet break free. Observations back up this picture, and they also show variety. The brief, intense flashes of gamma rays are usually followed by an afterglow that fades across 10th ray, optical, and radio wavelengths. That afterglow is useful. It tells astronomers about the material around the star and the galaxy hosting the explosion. In everyday terms, the afterglow is like the glowing embers and smoke you can study after a bonfire to learn what kind of wood was burned. Detecting the afterglow lets scientists locate the event, study the environment, and learn how the jet interacted with surrounding gas. There are practical reasons to care about these cosmic fireworks. For one, they are natural laboratories for physics under extreme conditions, places where matter and magnetic fields behave in ways we can't reproduce on Earth. They also act as beacons that illuminate the far universe, helping astronomers study galaxies that would otherwise be too faint to see. And while the idea of a gamma-ray beam hitting Earth sounds dramatic, such a direct hit would require a very unlucky alignment and a star unusually close by, so the odds are vanishingly small. Still, it's comforting to know that Earth's atmosphere is a great shield. A little cosmic humor: nature likes to hold its loudest concerts very far away and with a lot of security at the door. Observing deaths, light, neutrinos, and gravitational waves. A collapsing giant announces itself in several different ways, and each messenger brings a different clue about what happened at the star's core. Light, everything from radio waves to the highest energy gamma rays, carries the show that everyone can see with telescopes, but it can also be delayed or altered by the star's outer layers. Telescopes that look in different kinds of light act like different pairs of glasses. Radio dishes reveal the slowly spreading shock, optical telescopes catch the bright flash and fading glow, and 10th ray or gamma ray instruments expose the hottest, most energetic bits. Think of it like watching a bonfire: the glare tells you it burned brightly, while the smell and smoke tell you what actually combusted. Similarly, different wavelengths of light reveal different parts of the explosion. Neutrinos are tiny, nearly invisible particles that stream out from the collapsing core almost unimpeded, carrying information from deep inside where light can't get out at first. They are the stealthy messengers, able to pass through an entire planet almost as if it were empty air. To catch these ghosts, scientists build enormous detectors, huge tanks of super clean water or vast volumes of Antarctic ice full of sensors. When a neutrino finally does bump into an atom, it makes a small flash of light that those sensors can see. Because neutrinos escape directly from the core, a burst of them can arrive before the first bright flash of light reaches us, providing an early peek at the catastrophe's heart. It's like getting an advance text message from a friend before they post the selfie. Gravitational waves are ripples in space itself, created when mass moves in a lopsided or violent way. Picture a smooth blanket getting flicked. The ripples travel outward and stretch and squeeze anything they pass through by an almost unimaginably tiny amount. To sense those tiny changes, observatories use laser beams and long empty tunnels to compare distances with extreme precision. Multiple facilities working together confirm a real signal and help pinpoint where it came from. Detecting gravitational waves from a dying star can reveal how violently the core recoiled or tumbled, information that light and neutrinos alone cannot provide. If neutrinos are the early text and light is the selfie, gravitational waves are the creak of the floorboards that tell you someone just slammed the door. Putting these different messengers together gives a much fuller story than any one alone. Neutrinos tell us about the inner engine and the conditions at the very center. Gravitational waves reveal the shape and dynamics of the collapse. Light shows the outer layers, the material thrown into space, and the chemical elements produced. Practically, this means astronomers can time observations more effectively, point telescopes where they need to look, and test ideas about how elements like oxygen and iron are forged. It also helps answer big questions about how matter behaves at extreme densities and what makes some explosions form black holes instead of leaving behind a neutron star. In short, listening to the light, the ghostly particles, and the ripples together is like having a full set of witnesses to a cosmic whodunit, and sometimes those witnesses disagree, which keeps scientists busy and entertained. The aftermath: enriching galaxies with heavy elements. Massive stellar explosions throw the products of a star's life far and wide, and those products are the heavy elements that make up planets, people, and things like smartphones. Stars fuse light atoms into heavier ones while they burn, building up elements such as carbon, oxygen, and iron in their cores. When the star explodes, that material is blasted into space. Some elements, like iron, are cooked slowly inside stars. Others, like gold and platinum, need a far messier process that happens when neutrons slam into atomic nuclei very quickly during explosive events. Neutron-star collisions, where two dead stars spiral together and smash, also spray out a rich mix of these very heavy elements, so the universe has more than one kind of cosmic kitchen. The matter expelled by explosions comes out as hot gas and tiny solid grains of dust, and these mix into vast clouds between the stars. Think of those clouds as the pantry of a galaxy. Pockets of enriched gas and dust get pulled together by gravity, cool down, and eventually form new stars and planets. Meteorites that fall to Earth contain tiny pre-solar grains, solid bits that predate our Sun, and those grains carry the fingerprint of ancient stellar events. Light from glowing supernova remnants shows bright signatures of elements such as oxygen, silicon, iron, and nickel. Astronomers read those signatures like a barcode to know what was made and thrown out. Everyday materials owe their existence to that cosmic recycling. The carbon in your cells, the oxygen you breathe, the calcium in your bones, and the iron in your blood all began inside stars and were spread by explosions and winds. Soil gets its mix of metals and minerals from rocks that were themselves built from star stuff, which means nutrients that support crops ultimately trace back to stellar processes. Even jewelry and electronics have a celestial origin. The gold in a ring and the silicon in a computer chip were once part of the interiors of stars or the debris of stellar collisions. It's a bit comforting, and a little funny, to realize that the copper wire in a toaster has more in common with a star than with a garden hose. The enrichment process keeps galaxies chemically alive and changing. New generations of stars form from gas that contains more heavy elements than the gas that made older generations, and those differences affect how stars shine and how planets form. Observations show regions rich in heavy elements often produce planetary systems stuffed with rocky worlds. Dust grains that formed in explosive ejecta act as seeds for planet formation, clumping together like flour particles in dough. So the next time you hold a handful of soil or look at a metal coin, remember that those materials are chapters in a long chain of creation and destruction on a galactic scale, messy, spectacular, and ultimately the reason we get to enjoy coffee, smartphones, and the occasional bit of bling. Case studies: famous massive stars and their fates. Betelgeuse is a red supergiant in the constellation Orion that astronomers watch closely because it offers a clear picture of how a very large star behaves near the end of its life. Red supergiants are cooler on the surface but enormously bloated, like a hot air balloon compared with a compact camp stove. When these stars run out of fuel in their cores, they can no longer hold up against gravity and the core collapses, which usually leads to a bright explosion called a supernova and leaves behind either a neutron star, a city-sized object with absurd density, or a black hole, which traps even light. Rigel, by contrast, is a blue supergiant, much hotter and more compact than Betelgeuse, and it follows a slightly different script toward collapse. Blue supergiants burn their fuel faster, like a car with a powerful engine that guzzles gas. They can end their lives in spectacular blasts as well, but details depend on how much mass they lose along the way. Mass loss matters a lot. Think of a star shedding layers like someone taking off sweaters in a sauna. What's left underneath changes what happens next. Antares is another famous red supergiant notable for having a smaller companion star nearby, and that companionship affects fate in surprising ways. Binary partners can steal mass, trigger eruptions, or even merge, changing whether the final collapse produces a neutron star or a black hole. VY Canis Majoris is an extreme example of a monster star that has been throwing off huge amounts of material. It's so unstable it looks like a messy kitchen after a cook-off. That material forms a cocoon that shapes the final explosion and the glowing remnants left behind. Eta Carini gives a vivid example of violent behavior before the final act. It's a very bright, massive pair of stars that once underwent giant eruptions, throwing off so much gas and dust that it now sits inside a dramatic, lobed shell. These eruptions are warnings that the internal balance is shaky. When the final collapse happens, the expelled material determines how the light from the explosion will look. In rare alignments and under the right conditions, a collapse could even launch a narrow, extremely energetic beam called a gamma-ray burst, but that requires specific circumstances and direction. Wolf-Rayet stars are another group to watch. They have lost their outer hydrogen layers and are essentially stripped cores blowing off fierce winds. They often end life in bright, energetic explosions and are sometimes surrounded by beautiful pinwheel dust patterns when paired with companions, such as the famous pinwheel around WR104. A clear, practical example of what these cases teach us comes from one nearby supernova that was observed up close. A blue supergiant exploded and its blast lit up rings of gas that had been shed earlier, like a car's headlights lighting fog banks created by past activity. That glowing fog told astronomers about how material was ejected before the collapse and how the explosion's shockwave moves through space. Such observations are the best laboratory we have for testing ideas about how elements heavier than iron get made and distributed through galaxies. Studying these famous stars is not just academic, it explains where the elements in everyday objects and bodies come from. The calcium in your bones and the iron in your tools were forged in the hot furnaces of massive stars and scattered by their deaths. That is literally true, and a little poetic. So while massive stars live fast and die dramatically, their debris seeds future generations of stars, planets, and even life, which makes their noisy, messy ends important for everything from smartphone materials to the stuff in your kitchen cupboard. Simulating stars. How scientists model stellar evolution. Scientists use computer models to copy how a star lives, from its gentle youth to its dramatic end, by putting known physics into code and watching what comes out. They feed a model simple starting facts like how heavy the star is and what it's made of. These are the recipe and the ingredients, and the program follows how gravity squeezes the gas, how heat fights that squeeze, and how tiny nuclear reactions turn lighter atoms into heavier ones to produce light. Instead of messy kitchen smells, you get streams of numbers that tell you the star's temperature, size, and what elements are present at each layer. This is practical. Change the mass or the mix of elements and the model might predict a calm white dwarf or a violent collapse, much like swapping flour for almond flour changes a cake. Many models act in one dimension, treating the star as a set of concentric shells like layers of an onion, because that makes it possible to run a whole star's life on a normal cluster of computers. One popular toolkit used by researchers is called MESA, which lets scientists try different ingredients and cooking times without burning real stars. For messy, short-lived events where motion in all directions matters, such as turbulent boiling inside a star or the shock of an exploding core, teams build three-dimensional simulations that solve how gas flows and mixes. These need supercomputers and a lot of patience. Think of 1D codes as long cookbook experiments and 3D runs as up-close videos of the oven exploding. Both are useful, but they answer different questions. To keep these virtual stars honest, modelers compare them to real observations. The sun gives especially detailed feedback through measurements of its sound waves, which reveal its inside structure much like an ultrasound. Observations of groups of stars, spectroscopy that reads chemical fingerprints, and the bright flashes of supernovae all serve as taste testers for the models. Laboratory measurements of how fast specific nuclear reactions proceed are another ingredient check. Particle labs measure the reaction strengths that the codes use like chefs measuring teaspoons. When models and observations disagree, scientists tweak assumptions about mixing, winds, or magnetic fields until the virtual roast matches the real one. Uncertainty is part of the fun and the frustration. Processes that mix material inside a star, such as convection, behave like turbulent cream stirred into coffee and are hard to describe with simple rules. Rotation and magnetic fields add more twists, literally. To cope, researchers run many versions of a star changing one thing at a time, which is like testing a dozen cookie recipes to see which keeps its shape best. Advances in computing and shared community codes have sped progress, but some big questions, like the exact trigger of a collapsing core that makes a supernova, still need better three-dimensional modeling and smarter physics. In the end, simulations give useful, testable predictions about whether a star will fade quietly or end with a bang, and they let astronomers plan observations with a much clearer idea of what to expect. Open mysteries and active research questions. Astronomers still don't fully understand exactly how the cores of very heavy stars explode at the end of their lives. One big question is how a collapsing core turns into the outward blast we see as a supernova. Tiny, nearly invisible particles called neutrinos carry away enormous energy. They act a bit like a leaky heater trying to warm a room. Most of the heat flows out, but a little bit that stays behind can change everything. Whether that little energy is enough to push the outer layers outward depends on messy, three-dimensional motions inside the star, boiling like turbulence, swirling rotation, and magnetic corkscrews, none of which are easy to simulate or observe directly. Mass loss before the final collapse is another major uncertainty. Stars can lose their outer layers slowly through winds, or rapidly when a companion star strips them away in a close binary system. Think of it like haircuts: some stars get a tidy trim, others get shaved bald by a partner. The result determines the visible type of explosion and what elements are exposed. Observers see different spectral signatures. Some supernovae show hydrogen, others do not, and matching those signatures back to the star's prior grooming habits is an active puzzle. Metal content of the star's outer layers also affects wind strength, but how this mixes with binary interactions across different environments remains unclear. Some massive stars might meet a spectacularly different fate known as parainstability. In plain terms, high-energy light inside a star can spontaneously turn into matter and antimatter pairs, softening internal pressure and triggering a runaway collapse and explosion that can completely unbind the star, leaving nothing behind. Whether a given star follows that route or avoids it depends on the star's inner chemistry and mass loss history, and pinning down the boundary is tricky. Relatedly, astronomers debate what powers superluminous supernovae, those extremely bright explosions, because several engines could do the job: a newly born, fast-spinning magnet with huge magnetic fields, collisions between shells of previously ejected material, or a very energetic collapse. It's like trying to decide whether a car's speed came from its engine, a downhill slope, or being pushed by friends. What kind of compact object survives is also under active study. Sometimes the core collapse leaves behind a neutron star, an ultradense ball of neutrons. Other times it produces a black hole, an object so compact not even light escapes. The tipping point is sensitive to how the star's core behaved in the final seconds, how much material falls back after the initial blast, and the physics of matter at extreme densities, the equation of state, which is not fully known. Observations of pulsars and gravitational waves provide clues, but translating those clues into a clear rulebook for remnant formation is a work in progress. And yes, the possibility that the explosion itself is lopsided, throwing debris preferentially one way, adds further complications, like a poorly aimed confetti cannon. The cosmic recipe for heavy elements poses yet another open question. Elements heavier than iron, think gold and uranium, form in explosive, neutron-rich environments. Competing ideas propose that these elements are forged in the guts of some core collapse supernovae or during violent mergers of neutron stars. Stellar explosions leave fingerprints in the chemical makeup of later generations of stars, and careful measurements of those fingerprints help narrow the options. Still, connecting specific abundance patterns to precise astrophysical sites is like tracing a family recipe after a potluck. You know who brought the dish, but not all the ingredients. Finally, observational limitations and computational challenges slow progress. Capturing the very early light from a collapsing star, catching neutrinos from a nearby explosion, and detecting gravitational waves from asymmetric collapses would give priceless direct information. Meanwhile, simulating the multiphysics problem, fluid motion, magnetic fields, neutrino transport, and nuclear reactions, requires enormous computing power and clever approximations. Better telescopes and detectors are on the way, and improved models are being developed, but the universe keeps throwing curveballs. Scientists love a mystery. It keeps the coffee machine busy and the whiteboard markers in demand. Why massive stars captivate our imagination. Massive stars burn far more fuel than our sun and shine with a raw, visible power that grabs attention even across vast distances. Their light can outshine whole neighborhoods of stars, making them beacons in the night sky, and that brightness is only the beginning of what makes them so fascinating. Inside their cores, atoms are fused together into heavier atoms in a process like a cosmic kitchen, and this steady churning builds the very material that will one day become planets, jewelry, and the iron in our blood. Think of a massive star as a giant factory. It keeps turning simple ingredients into complex products, and when it shuts down the final assembly line, the leftovers scatter everywhere. The ending of a massive star's life is dramatic and theatrical. Some end in titanic explosions that briefly rival the light of entire galaxies, while others collapse into tiny, extremely dense objects that behave in ways our everyday intuition cannot handle. A supernova is like a fireworks finale on a universal scale, bright, noisy in energy if not in sound, and spectacular to watch. When a star compresses into a neutron star, it becomes a city-sized object with more weight than a mountain packed into a spoonful. That contrast is as hard to imagine as fitting an elephant into a bathtub. Black holes, which can form from the most massive collapses, tug at space itself so fiercely that not even light escapes, and they make for dramatic plot devices in movies for good reason. People are drawn to these stars because they connect the remote and the personal. The calcium in our bones and the oxygen we breathe were cooked inside earlier generations of massive stars and spread through space by their violent deaths. Your smartphone, wedding ring, and breakfast cereal all owe something to those stellar factories. It's a neat, slightly poetic fact that ties everyday objects to explosive cosmic events. Even on a clear night you can tell stories to friends under the stars and point out that the atoms in their bodies once passed through a process like a stellar oven. That thought mixes science with a warm, human sentiment, and sometimes a little awe sounds like a good laugh around a campfire. Curiosity is another strong pull. These stars test the limits of physics in extreme conditions you cannot reproduce on Earth. Pressures and temperatures inside them are so high that matter behaves strangely, and astronomers learn about basic forces by watching how these stars live and die. Telescopes that detect different kinds of light, visible, 10th rays, radio, act like different senses, revealing layers of behavior and unexpected surprises. The combination of beauty, mystery, and practical importance keeps both scientists and the public hooked. And if you enjoy a good plot twist, massive stars provide the happiest, saddest, and most explosive chapters in the cosmic story. We started with clouds of gas that squeezed together like fog turning into a raindrop, watched giant stars light up like cosmic ovens, and saw how those ovens cook simple stuff into heavier ingredients. Think of the star as a baker turning flour into bread. Big stars burn fast, like a bonfire that eats its wood in one wild night, and when they run out of fuel they explode in a spectacular fireworks show that spreads those cooked elements across space. Those scattered bits become the building blocks for planets, trees, and even you, so yes, you really are made of stardust, which is a much cooler family origin than from a mall. Sometimes what's left is a tiny, super-dense ember or a space so hungry for light it swallows everything nearby. Both are the dramatic leftovers of that final blast. If this cosmic life and death story sparked your curiosity, give the video a like, subscribe for more space tales, and tell me in the comments which part amazed you most. Next time we'll dive into black holes and the strange afterlives of stars, with simple visuals and a few more bad puns. Keep looking up, there's always another story written in the stars.